Welcome. So now we're going to be talking about continuity. And limits are going to play a part in our definition for continuity. And that's why this is part of limits still. So continuity at a point, this is just an intuitive definition. This is just so that you can get an idea in your head. It's a description. It's never going to be a justification. So any function y equals f of x whose graph can be sketched in one continuous motion without lifting the pencil as an example of a continuous function. You can never use that as a justification, right? Does not really prove anything. Excuse me, it's just a description, right? So it gives you a description of what a continuous or discontinuous function looks like, right? It's continuous if it will look continuous if you can do it without lifting up your pencil. If you had to lift up your pencil, it probably has a discontinuity, right? But it's not going to be it's not our definition. It's not our way to prove that, right? It's just a way so that you can visualize it. Let's do a little bit more visualizing here. All right, so continuity at a point, we're going to find the points at which our given function is continuous and the points for which it is discontinuous. Okay? So our graph's a little pixelated, but just imagine it's a nice smooth curve and a line. Right? It appears that they're at the endpoints there. Let us assume that those are points. There's nothing indicating there's any kind of hole or anything at our endpoints there. And I had these up for a reason, but we haven't gotten to the reason yet. Mostly it's just a point to something on the graph. All right, so when we're talking about an interval of something where something occurs, we're going to use x values only, whether it's we want to know where a function's increasing or decreasing, continuous, discontinuous, anything else you can think of to describe about a function that would involve an interval. You're always going to use the x values, right? Not the y. So where's our graph here? Continuous. And so notice there's nothing negative. There's no negative values. Our graph appears to start at 0. Right? So let's assume that it is an endpoint there at 0. Right? So that's where our graph begins. Right? We'll put a bracket there. We'll include 0 in our continuity here. And then we'll decide if, actually, you know what? Let's use parentheses. So let's use parentheses, and we'll think about whether we should use a bracket or not after we look at the formal definition of continuity. And so our function continues. It's a nice little curve there, a very lovely pixelated curve, and then it just stops right there. Right? So our function is continuous between 0 and 2. And then there's a break in the graph. It just stops. It picks up again over here at 3. Remember, the union there means and. And we're going to assume, since there's no arrows, that our function stops. I think that's a safe assumption without any arrows there. Right? And so that point is at 5. Looks like it's 5. So, by the way, notice there's a little mark here. I think it's part of the function right here. I can't point, I forgot. You can't see me pointing. But that little mark there looks like it's just part of the function, not something on the coordinate plane. Looks like the lines I've marked are spaces on that coordinate plane, right? Just to kind of make that clear there. Right? So in between 2 and 3, we have this giant break in the graph, right? It just stops and then picks up again at 3. So our function here, our graph, is discontinuous between 2 and 3. Let's take a look at the formal definition of continuity, and then let's come back to our diagram here and see if we should include the endpoints as being continuous or discontinuous. Where should they be? So we have two definitions for continuity. One is when we're looking at an interior point, and one is when we're looking at an endpoint. And this is in your notes, right? And we're going to add a little bit here to your notes just to make it clear. So at an interior point, a function y equals f of x is continuous at an interior point C of its domain. So what is that? We'll come back to what C of its domain means in a moment. All right? Let's look at the rest of the statement, and then we'll come back to C of its domain. If the limit as x approaches C of f of x equals f of C. Right? So what is that saying? Right? That's telling us that a function is continuous if the value of the function at C, actually let's put the limit first. The limit of the function at C of the function as x approaches C equals the value of the function at C. Right? If you want to even, well, you should probably put the sentence in there so that it makes sense, right? But here's our little pictorial explanation there, or symbol explanation, right? So if the limit as x approaches C of f of x equals f of C, what that means, the function's continuous, and this is only for an interior point, if the limit of the function as x approaches C equals the value of the function at x equals C. Or excuse me, when x equals C. Or we can just put at C. Right? So if the value of f of C and the limit are the exact same thing as x approaches C, then our function is continuous. And that's going to be part of the definition we use, part of our requirements that we're going to use to determine if functions are continuous or not. All right, so why does it say C of its domain? When we're looking at continuity at a point, only consider values that are in the domain of the function. All right, so we're gonna be looking at values that are actually in the domain of our function there for continuity. And we'll look actually at continuity in two different ways. But that's what that C of its domain. And that we're right now considering only points that are in the domain of the function. What if you're an endpoint, right? Now an endpoint can't have a limit, right? Can't have a two-sided limit because it's missing a side, right? If you're the left endpoint, you have a right-hand limit. If you're the right endpoint, you have a left-hand limit, but you don't have the other, right? Because if you're on the left-hand side, that's it. If you're the endpoint on the left-hand side, that's it. There's nobody coming from the left, right? You're the end. Right? So for endpoints, a function y equals f of x is continuous at a left endpoint, or is continuous at a right endpoint of its domain if, and this is that's our right-hand limit. It's a little small there. If the right-hand limit equals the value of the function. And that's for, of course, if you're a left endpoint. Squeeze that in there. And if you're a right endpoint, it's got to be the left-hand limit equals the value of the function. So now let's go back to our handy dandy little diagram here. All right, so should we consider our endpoints? Right? And they have to go either under the continuous or the discontinuous. They can't be part of both. All right, so let's take a look here. All right, so here is that's the left endpoint. All right, so it looks like f of 0 equals 0. If you know, kind of deal with the pixelating there. Looks like f of 0 equals 0. As we come from the right-hand side, the limit as x approaches 0 from the right-hand side is also 0. Right? So for our left endpoint, f of 0 equals the limit as x approaches 0. So then our left endpoint is continuous. And so we can take away the parentheses and we can give him a bracket. You're included, 0. You get to come along. All right, 2 is also an endpoint. Right, this one is a right-hand endpoint for that little piece there. Right, and so we have a right hand. Well, looks like, oh, that's right, it keeps going up here. Let's call that 1, 2, 3, 4. All right, so f of 2 equals 4. And notice as we're coming from the left-hand side, the limit as x approaches 2 from the left-hand side also equals 4. All right, so here, f of 2 equals the limit as x approaches 2, so that's continuous too. All right, so 2, you get to come along as well. We're not going to exclude you. And then let's look at 3. Oops, I'm going to write in another color because that's a lot of red over here. All right, so over here we have another left-hand endpoint. I could really use some more space, so this can maybe go down, possibly. There we go. All right, so f of 3 equals 0. And as we're coming from the right, the limit as x approaches 3 is also, oops, we need that, is also 0. All right, so this is also continuous. So we can get rid of that parentheses. And then as we're coming, this is our right hand right here. So we have a right hand endpoint. Right, so we're coming this way from the left. Value of the function there, let's call that 2.5. I guess so. All right, so f of 5 equals, or excuse me, negative 2.5 equals negative 2.5. And as we approach from the left, the limit as x approaches 5 is also 2.5. All right, so here again, I'm going to move my word continuous since we're going to use it for both. F of 5 equals the limit as x approaches 5. So both of these are also continuous. And you might think, won't the limit, always be coming from one side if we've got a little continuous piece there? Well, the limit might exist from the right or the left. The problem might be the value of the function not existing. We'll see some examples later on, and we might see somewhere the problem is the value of the function, not the limit so much. All right, so we're continuous everywhere from 0 to 2 because our limits from the left and the right existed, and they were the exact same thing as the value of our function at those endpoints. And then we're just discontinuous between 2 and 3. Everything between 2 and 3. They're not included. So now we've looked at continuity interior, but on an interior point and at an endpoint. And I'm going to pass that, and we've already gone over this. By the way, this is in your notes and the previous page, and you should add what I put in so that it makes sense. It's an explanation, so you don't look back at it, look at all the mathy words, and go, I don't know what this means. I don't remember. Right? We've got that explanation there, and that's going to help you, especially the stuff in blue. All right, so this is the absolute formal definition, and this is what's going to be required. All right? A function is continuous at a left endpoint or is continuous at a right endpoint of its domain. All right, so we've already gone over, we've already talked about interior, right? If the limit is equal to the value of the function, we're good. Let's talk about a little bit more about endpoints, because we said they won't always be included. They won't always be continuous at an endpoint. So all of these things have to happen. All right, so a function is continuous at a left endpoint or continuous at a right endpoint of its domain if, let's talk about the left endpoint. First of all, f of a is defined, right? So that left endpoint has to be defined for the function. It can't be a hole. The limit as x approaches a from the right exists. Okay? Just a little reminder here, this is our right-hand limit. Because this is the left endpoint. And the limit as x approaches a from the right has to equal the value of the function. Okay? So we went over that in that definition there, but this more clearly lays it out. Right? So we're looking for all three things to be true. If anything's not true, then that left endpoint is not continuous, and it doesn't get to be, we're not going to include it in our continuous portion. Let's look at the right-hand side. So f of b has to be defined. Right? B is going to be our right endpoint. The limit as x approaches b from the left, this is our left-hand limit. Endpoints only have a right-hand limit or a left-hand limit. If you're on the left, you have a right-hand limit. If you're on the right, you have a left-hand limit. And the limit of f of x as x approaches b from the left has to equal that value of the function. So thus, the function f of x is discontinuous not because it fails to exist at x equals c, but because f of c is not equal to the limit of f of x as x approaches c. Right? That's going to be the key. Does it exist, and does it equal the limit? Right? So what we might have, our point might exist. Right? We might have, it might be that so reasons that we won't be continuous at a point, a left end point or a right end point. Maybe you have a hole at your left end point and your right end point. Right? So your function is not defined there. Maybe it's defined, but it's not the point. So as we follow, it's not what the function is approaching as x approaches some value. It's some other point, right? And then the limit and the point don't match, right? So any of those things could cause our endpoint to be our function to be discontinuous at those endpoints. So we're always going to use that when we're talking about discontinuity. And matter of fact, we're always going to be discontinuous at an endpoint, right? Because we've got a break in somewhere in the graph. Or at an interior point, right? If we have a hole in the graph. If a function f is not continuous at a point c, we say that f is discontinuous at c, and c is a point of discontinuity of f. Note that C not be in the domain of F. Right? So if we're talking about the whole function, we want to know is the whole function continuous, we're going to consider values that are in the domain. We're not going to consider certain types of discontinuity. I shouldn't say that. We'll come back to this. I want to make, so don't worry about this for right now. Matter of fact, well, I'm not going to erase it because you might want it. But let's not talk about this right now, right? Because it's not a key point right now. What is a key point is whether our function exists and whether our limit exists from the right-hand side and the left-hand side for right now. And we'll come back to it. Right? So when we're talking about a point of discontinuity, we might have a hole in the graph, right? So it's not in the domain, right? But that is going to be a discontinuity. When you're plotting a function, if you pick up the pencil or pen, then you've made a discontinuity. Wherever you have a continuous line, i.e. you don't pick up your pencil, you have a continuous function or part thereof. Okay? So that's just so that when you're trying to figure it out, right? That quick summary helps you figure it out. But it will never be a justification, right? It's not a mathematically provable thing, right? You could just pick up the pencil because you dropped the pencil. Oops, it's not continuous. No, it's still continuous. You just dropped your pencil. Right? But that fact that the limit and the our value of our function have to be the same, that's what's going to tell us whether we're continuous or discontinuous. Most of the techniques of calculus require that functions be continuous. Remember to show that the function is continuous first. And I want you, did I put that in your notes? No, I'm looking down at them. And I do not see them in your notes. I want you to put them in your notes. All right? And put a big star next to it and a little hint on AP. Right? And let's write this under here. You must state, and this will be true not just for AP, but we'll talk about AP right now. So you must state a function is continuous, because I'll hold you to it too, as would any college class, before you use any technique requiring continuity. Okay. If you don't say it's continuous, you're not allowed to use a technique that requires continuity. And it has to be, by the way, the formal definition. The function, the value of the function, the limit being the same. All right, so let's take a look at our we got one and two sided limits here. Let's take a look at where we might have some discontinuities. Right, so this function has discontinuities at x equals 1 and x equals 2. It's continuous at x equals 0, right, because the value of the function right here, f of 0 equals 1. And if we look over here, the limit as x approaches 0 from the right-hand side is also 1. All right, so that's a continuous endpoint right there. We're good there. We're also continuous at x equals 4 for the same reason. All right, so here, f of 4 is, I'll call it, that looks like 1 to me, is 1. And as we approach here from the left-hand side, the limit as x approaches 4 is also 1. All right, so our endpoints here are continuous. So we're continuous at this endpoint, and we're continuous at this endpoint. Right? And that's because the one-sided limits match the value of the function. By the way, this is in your notes, right? And you should add in the red words. Right? So for anything less than 0, for c less than 0, and c greater than 4. These points are not in the domain of f. So when we talk about continuity, we're not going to talk about points that aren't in the domain of f. Right? We're going to stick between points that are at between 0 and 4. Right? Now let's take a look at our points where we are discontinuous. We are discontinuous at 1. Right? So here we're for a couple of reasons. We're also not continuous at that point there. Right? So here the limit as x approaches 1 from the left does not equal the limit as x approaches 1 from the right. Right? So we do have a break in the graph. We're also not continuous at that endpoint either. Right? Oh, excuse me. No, yes, we are. We are continuous at the endpoint, but only from one side and not from the other side. So, and that one picks up again. So here we have a little problem, right? Because, well, if we're so it's not continuous. Notice if we're coming from the right-hand side here, we have a hole in the graph. But if we're coming from, the left-hand side, we have a hole there. As we're coming from the right-hand side, that part's defined. However, since that point there is used twice, so notice at 1 there, we're using it both as a right end point and for one segment and a left end point for the other segment. You can't say it's discontinuous for one piece and continuous for the other. That just blows that all apart. All right, so if there was no f of 1, if it didn't pick up again till f of 2, well then 1 would have been continuous as an endpoint. If f of 1 happened to be 0. But because those right and left aren't the same, 1 is used twice, 1's got a hole, that blows that one altogether. So we got a discontinuity there at 1, okay? And that's because the right and left hand limits are not the same. We can't even use a one-sided limit on that one. We also have a discontinuity, right? Let's add this in here. The limit as x approaches 2 is equal to 1, right? So let's get rid of these arrows here. We already know that you blew at 1. We're good here at 0, you blew at 1. So here as we approach from the left-hand side and the right-hand side, our limit is clearly 1. But f of 2 is equal to 2, and 1 does not equal 2. Right? So we have a discontinuity there at 2. Right? So now we only considered points between 0 and 4 because that's as far as the function went. That's what this means over here. My green words. Right? So for continuity, only consider values that are in the domain of the function. Right? So you might want to draw a little arrow, because it's at the bottom of the page, that diagram. Right? And draw to where it says we only use between 0 and 4. We didn't use less than 0. We didn't use more than 4. How can you talk about continuity if there's no more function? Right? So that's what that means about that in the domain of the function. If the function stops, we can't look any further to that past that point, right? Or past that part of the function. So that's what that means. Told you it's better with an illustration. Right? And that's why I was waiting for a graph that illustrated it. And fortunately, you've got it in your notes and it's on the same page. I must have been really super thinking over the summer when I made the notes. So types of discontinuities, if you go to the next page, these are all illustrated for you. And then I do want you to write over the word write over any of these over here. But our essential discontinuities, these are non-removable. We can put it right here. Right? So we have our removable discontinuities. You can fill in the hole. Right? So I can add 1 point to my function, make it a piecewise function, fill in my hole, and I've removed the discontinuity. We will look at that in a later lesson. But there's nothing I can do about a jump discontinuity, an infinite discontinuity where I have a vertical asymptote, or this is called an oscillating discontinuity. Right? Now why would this be continuous? You probably wouldn't think that was discontinuous. And it's discontinuous because the limit doesn't exist. If your limit doesn't exist, that's one of our reasons a limit fails to exist, right? You're oscillating, you're not headed towards anything, you're just going back and forth. And remember when I showed you that one graph, it just looked like a sea of red? That was sine x over x. No, it wasn't sine x over x, because that one, not as x approaches 0. What was that graph? Well, we had a graph that just oscillated. It's probably this one. Y equals sine 1 over x. That was the graph. So if your limit doesn't exist, and that was one of the reasons the limit fails to exist, it's oscillating. Right? Another one, the right-hand side doesn't match the limit as you come from the right, doesn't match the limit as you come from the left. The right-hand limit is not equal to the left-hand limit, and that would be an example of a jump discontinuity. And we can actually write that in. So the limit as x approaches whatever our point is from the left does not equal the limit as x approaches that point from the right. Right? And that would be a reason you could say that your function was discontinuous if you have a jump discontinuity. Right? An infinite discontinuity was if your function did not approach a finite value, but it increased or decreased without bounds, right? It just kept growing without bounds, or in either the positive direction towards infinity or the negative direction towards negative infinity, right? Our limit did not exist, right? So we have a discontinuity when we have a vertical asymptote, again, because the limit fails to exist. So it's discontinuous because the limit fails to exist. There's another way of saying the limit does not exist. Right? So here are the reasons that the bottom ones are discontinuous. The top ones are discontinuous as well. And let's fill in why they're discontinuous. All right, so for our removable discontinuities, the limit as x approaches c does not equal f of c. That's why that's discontinuous. All right, so now you've got all your reasons. So now when you see another function that looks like one of these, you'll know this is why it's discontinuous. And by the way, that for removable discontinuous, it applies to both graphs. Oh, actually, I'm sorry. This one applies to this graph. Do you know what reason applies to the one on the left-hand side? F of c does not exist. Right? There's a hole. So if f of c doesn't even exist, how could it possibly equal to the limit? Right? So don't use the limit doesn't match the value of the function if the value of the function doesn't even exist. Right? Just say the value of the function doesn't exist. Right? So there's our types of discontinuity. Right? So definition of continuity. Right? So here is what we're going to use for continuity at a point. A function f is continuous at c if the three following conditions are met. And it's very similar to our right and left hand endpoint, the requirements for the left endpoint and the right endpoint, except we don't have a one-sided limit, we have a two-sided limit. All right, so first of all, f of c is defined. If f of c is not defined, you should say a function is discontinuous. And why? Because f of c is not defined. Second, the limit of f of x exists as x approaches c. If the limit does not exist, you should say the function is discontinuous because the limit as x approaches c of f of x does not exist. And if the limit exists and the value of the function exists, but they're not the same thing, you should say that the function is discontinuous because the limit as x approaches c of f of x does not equal f of c. All right? All three of those things have to be met. And these are going to be the reasons whenever you're going to tell me that a function is continuous or not discontinuous, you have to show these exist. or these hold. So let's write that. Must show all three are true for continuous, or state the one that is not true for discontinuous. Right? This is all of our reasons in a handy dandy little graph. And by the way, this is the whole big idea of this entire lesson. There's more, but this was the big idea. So continuity on an open interval. A function is continuous on an open interval. What does that mean, open interval? No endpoints. Right? We're not going between two values. A and B, if it's continuous, oh, I put it in the wrong spot, sorry. I meant to put that you're not considering the endpoints. That's why it's an open interval. I'm looking at the one, I'm thinking ahead to the one underneath it. So if you say an open interval, you're not considering the endpoints. If you say closed interval, that means you're considering the endpoints too. So if you're not considering the endpoints, you wouldn't use brackets, you'd use parentheses. So this would be brackets, and this one over here would be parentheses. A function that's continuous on the entire real line, negative infinity to infinity, is everywhere continuous. There's no endpoints at all, right? There's no stopping. You're looking at the entire thing. And there are functions that are continuous everywhere. And those are the ones you're probably most familiar with. And we'll talk about those in another podcast. Because I have some questions that you'll answer there. And I think, let me make sure that I have a whiteboard practice, and I think that this would be a really good place to stop, right? Because that next part I want to do all on its own, where we're going to look at whether functions are continuous or discontinuous. By the way, those those multiple choice questions that I just kind of showed after the whiteboard practice, those are not quiz questions for you to answer. Those are questions for us to discuss. I am probably going to have you either I'll do it in class, or more likely I'll record it, just in case someone's absent. You'll make a choice, and then you'll see if your choice was right, and I'll explain the choice, right? Because on that one, the explanation is really, really important. All right, so thanks for watching. Bye for now, and that's the end of this podcast.